That instrument there, those antennas there, are the ones that measure the vertical and horizontally polarized sferics, the crackle.
This is an electric field mill. It measures the charge in the atmosphere. During an intense storm, the atmosphere is supercharged. That helps meteorologists tell us when to take cover.
You know, anything that can give you another minute or two of warning, especially for tornadic storms, is terribly important. The one on the right is a Sferics experiment that measures the electric breakdown in the clouds. You hear it on your AM radio when you hear the crackles. What happens in this particular subdivision next week at 4 o'clock? You know, is my Alta tennis match going to be rained out? But I don't know that we'll ever get to that point.
In Marietta, Renee Starzik, CBS 46 News.
So we currently have operational LMA units at those 5 locations.
Welcome to the Severe Storms Research Center at GTRI. John Trostel is the director of the center, which has been in existence since 1999. Now, their mission is to find new ways to track and predict severe weather for North Georgia. Today, Trostel is explaining a large mapping array, or LMA, of data sensors currently in place to track lightning strikes.
There's some research right now that's looking at what are the trends in the lightning that's in the cloud-to-cloud lightning, and is that a precursor to the storms becoming severe? So can I look at the lightning trends and determine whether a storm will go tornadic or not? So that's very important research, especially here in what they call Dixie Alley. The array coverage will overlap, and so instead of just having data from Alabama and data from Georgia, we'll be able to track the storms as they go across the southeast and track them longer, track bigger storms, and determine more of their evolution.
Right now, there are 6 LMAs in place with the hopes of expanding to 10 sites soon to increase that detection range.
RF signals are picked up on the antenna and transferred down to the box here, along with a GPS signal for time stamping. And then they are filtered with a filter and then processed by this very small computer board. And that data then can come out over Ethernet and come back to our main computer, where we collate all the data and determine where the different signals came from. We'll be able to map this lightning in 3 dimensions as well as in time. So that data then we'll be able to both give to the National Weather Service, so they can use that to add to the utility of their radars.
Work now involves using the data to look at the charge in a thunderstorm in 3 dimensions. We can actually determine the layers in the cloud where a charge are breaking down. Also, we detect the intercloud discharges, and we discovered these intercloud discharges precede the cloud-to-ground lightning by about 15 minutes. And 15 minutes is enough time to get the warning out, so you get the kids and the adults out of the swimming pool, you get the adults off the golf course. Anybody outside has time to take shelter, because we can now provide the warning of lightning because we detect the intercloud discharge. That's the breakdown that occurs within the cloud about 15 minutes before the first ground strike. So, get the kids out of the pool, get the guys off the golf course, take cover.
Schultz at the University of Alabama in Huntsville, and I would like to talk to you today about lightning jump algorithm for the GOES-R geostationary lightning mapper using proxy data set. This is based off work started with Schultz et al. 2009 and 2011 that made or developed a lightning jump algorithm using lightning mapping array data, 3-dimensional lightning data, which is a ground-based network. They applied this algorithm to help that worked with a data set that would be similar to what we would see from the space-based satellite, space-based data. So we took that algorithm and applied it using this proxy data set that was developed using lightning imager sensor data and the ground LMA data to create a database of what splashes look like from space and from the ground. That database is then used to create this proxy data using statistical relationships where we used 2002 through 2011. What we did was we applied, we looked at two different verification methods as that can change the results. When we say results, I'm talking about our property detection and our false alarm rate. When we applied the algorithm, we had different tunable parameters that we're looking at to do sensitivity tests. We looked at the sigma threshold, which is a statistical threshold that the algorithm used. We looked at flash rate threshold, the time the algorithm spun up, and then for verification, looking at the report distance from the storm, as we know there can be error with that, and then our forecast period, and then with our database, the domain range that we use from the center of our network, and the spatial scale when tracking with the WITSI algorithm. Here we have some of the output from that we're tracking. Here we have our 5-minute flash counts, which on average 5-minute on a 1-minute basis, and then our reflectivity. And then for this, we tracked most use reflectivity base to track. We combine the lightning data and the radar data using this VIL flash rate density product. We tracked on that, and we can see our cells as you see here. And so we take these cell tracks or these cluster tracks, and those were our clusters that we would then apply our algorithm to. We applied the algorithm, we did some sensitivity tests, and so far what we have found is that the flash rate threshold and our sigma, or that statistical level that the lightning data must reach to say a jump has occurred, those seem to have the most influence to influence our probability detection and a false alarm rate to help use this in an operational framework. So we hope to go forward with this and tune the algorithm so that it can be used when we get the lightning data from the geospatial lightning mapper when GOES-R is launched in the next couple of years. Thank you.
I'm here with Jeffrey Stano, and he's going to talk about expanding operational uses of total lightning ahead of GOES-R. And Jeffrey, what is the premise of your research, and what did you find?
Well, what we're doing right now is, the organization I work with is called NASA's Short-Term Prediction Research and Transition Center. Our role is to try to work with unique and experimental data sets and try to bring them into the operational environment. One of the things that we're doing right now with that are using lightning mapping arrays. These are ground-based networks developed by New Mexico Tech. And this is a collaborative process where we're taking networks from across the country. Some of them are owned by NASA, some of them are owned by universities. And so it's a collaborative environment to bring these networks together. The goal is to try to introduce total lightning data into operations. These data are useful because in addition to just getting, unlike the National Lightning Detection Network, which gives you predominantly cloud-to-ground strikes, you can actually work with lightning mapping arrays to get the total lightning, intra-cloud and cloud-to-ground flashes. Now, it won't give you actual cloud-to-ground strike, but the advantage is you can look at the spatial extent of lightning, you can look at how a storm is updating in time, so it's rapidly intensifying, so it's a precursor to severe weather. What this activity has been doing, we've been working with several new partners across the country, working with Cheyenne, Boulder, Albuquerque, in addition to several Center Weather Service units, such as out in Houston, also up in Longmont, Colorado. And we're taking a lot of the efforts that we've been working with for the past 10 years, with say back in the Southeast, with Huntsville, Alabama, and that forecast office, and try to say, how do we use these data in operations? This then lets us get prepared for the GOES-R era, because we use these data as a proxy for the geostationary lightning mapper.
It's kind of hard to explain how important weather is to our job. I mean, it really affects everything we do.
In 2018, NOAA launches the GOES-S satellite, which takes its place in orbit as GOES-17. Working together with GOES-16, the two new geostationary weather satellites will provide constant watch over the United States and the Western Hemisphere, from the west coast of Africa all the way to New Zealand, helping monitor severe storms, wildfires, and daily weather patterns. Since its launch, NOAA's GOES-16 satellite has already demonstrated its critical capability for keeping our nation weather ready. Throughout the active 2017 hurricane season, GOES-16 delivered imagery with detail and clarity never achieved before, with 4 times greater resolution than previous NOAA satellites, and delivered this imagery faster than ever before, helping forecasters predict the path of a storm and where and when it will intensify. These accurate and timely forecasts allowed for emergency managers to prepare for evacuations, map flood areas, and save lives. GOES-17's geostationary lightning mapper monitors lightning flashes, including the in-cloud lightning most prevalent in severe storms, helping forecasters determine when a storm is forming, intensifying, and becoming more dangerous. Thanks to GOES-17, emergency managers will be equipped with more accurate weather predictions and faster warnings, providing a real impact, saving lives, and protecting infrastructure. Watching over Earth from 22,300 miles above, GOES-S will provide vital data to our weather-ready nation.